For millions of years, the Earth's climate has been governed by Milankovitch cycles. These are massive, predictable astronomical rhythms, changes in the planet's eccentricity, wobble, and tilt, that dictate our natural ice ages and the warmer interglacial periods in between. The most recent of these warm periods is the Holocene. For the last 11,700 years, this epoch provided a highly stable, predictable environmental baseline that allowed human civilization to develop. But over the last century, the exponential growth and technological capacity of a single species interrupted that ancient planetary rhythm. Geologists mark the end of the Holocene baseline on August 16, 1945. The detonation of the first nuclear weapons deposited a global layer of radiogenic fallout into the soil, creating a permanent, unnatural boundary in the Earth. From that point forward, human forcing overpowered astronomical cycles. We entered the Anthropocene, a geological epoch driven entirely by human activity. To see how this epoch functions on the ground, we have to look past global atmospheric markers and examine a specific physical test environment. This map outlines the Mahanadi River Basin on India's east coast. It covers over 141,000 square kilometers across the states of Chhattisgarh and Odisha. Throughout the Holocene, this basin operated as a continuous conveyor belt. It gathered rainfall and eroded rock from the interior highlands, transferring that water and physical earth down to the sea to build a resilient coastline. Today, geological processes that required millennia have been compressed into less than 80 years. The landscape is drying and fragmenting at an observable rate. This severe, localized compression of the timeline gives us undeniable empirical proof of the Anthropocene in action. By deconstructing the hydrology of the Mahanadi, we can measure exactly how human engineering has replaced natural climate as the primary driver of the Earth's physical shape. We begin the investigation at the absolute terminus of the basin, the Chilika Lagoon. Historically, this was a massive, thriving brackish water gulf where the river met the sea. The lagoon's spatial footprint has unnaturally shrunk from a historical spread of 1,500 square kilometers down to just 1,165. The vertical collapse is even steeper. Over the 20th century, the average depth halved from 3 meters to 1.6 meters as silt piled up. This hyper-sedimentation directly choked the ecosystem. In a matter of decades, 40% of the native brackish water species simply disappeared. As the mud accumulated, the tidal inlets shifted and depleted, physically cutting off the lagoon's ability to exchange flow with the open ocean. Without that saltwater exchange, the brackish gulf is rapidly converting into a stagnant freshwater lake, pushing the original marine ecosystem toward total collapse. Chilika's rapid shallowing is a terminal symptom of a much larger mass imbalance. To find the cause, we have to trace the failure upstream. Moving up from the lagoon brings us to the Mahanadi Delta, an arcuate or bow-shaped landmass covering 9,500 square kilometers. It was built by millennia of continuous river deposition. Despite increasing regional rainfall, the historical delta is actively sinking and shrinking inland. The coastline is being eaten by the sea. The data reveals a massive deficit in water volume. The river's average annual discharge plummeted from 66.8 billion cubic meters in the past to just 41.5 billion today. The collapse in physical mass is even more severe. In the early 1980s, the river delivered nearly 27 million metric tons of sediment annually. Today, that number has dropped to 10.7 million. That missing 16 million tons of annual sediment is the foundational armor the delta requires to withstand oceanic erosion and rebuild its shores.
The delta is failing because its raw geological supply line has been artificially severed upstream. If we follow that severed supply line deep into the upper and middle Mahanadi Basin, we reach the states of Chhattisgarh and Odisha. Here, we find the primary mechanism of sediment arrest, a sprawling network of human-built water infrastructure acting as concrete barricades across the watershed. This schematic maps the 851-kilometer river. Engineers have injected 253 dams, 14 barrages, and 13 weirs directly into the system. This network traps 66.7% of the basin's historical sediment flux behind concrete walls, preventing the earth from reaching the coast. The remaining water is subjected to unregulated extraction. Superthermal power plants and heavy mining operations divert vast volumes away from the main channel. By the time summer arrives, this extreme hydrologic intervention leaves the remaining river flow heavily polluted and entirely unfit for agriculture. Human engineering has fully replaced the river itself as the dominant geomorphological force shaping the landscape. This explosion of infrastructure directly tracks with the timeline of human demographic and economic expansion across the central Indian peninsula. Researchers map this to the Great Acceleration, a phase beginning around 1980, where human-driven data trends violently broke away from all linear historical patterns. This chart plots population and agriculture. Notice the exponential upward kink across the 45 basin districts exactly at 1980. This demographic boom triggered skyrocketing agricultural intensity, placing unsustainable biological stress on the watershed. Simultaneously, regional temperature anomalies mirror this exact post-1980 break. The basin's temperature is now rising at 1.1 degrees Celsius per century. That is double the Indian national average. The simultaneous 1980 acceleration kinks across hydrology, demography, and temperature prove that human consumption now fully dictates the physical trajectory of the basin. Permanently breaking a region's geological mass balance creates volatile, unpredictable climatic feedback loops that engineers cannot control. We see this clearly in the drastic increase in devastating floods, such as the catastrophic events of 1982 and 2008. These floods were driven not by natural monsoons, but by ill-coordinated reservoir releases that entirely overwhelmed the restricted channels. The region is now plagued by severe extremes. The basin experiences killer heat waves, temperatures soaring to 50 degrees, and highly abnormal fatal lightning strikes. On the coast, the weakened, sinking delta offers no resistance when battered by slamming severe storms and supercyclones. The natural buffer is gone. By attempting to violently control the basin's hydrology, human intervention has engineered a vastly more erratic and dangerous environmental system. What began with a microscopic nuclear baseline in 1945 has cascaded into the macroscopic, physical collapse of a 141,000 square kilometer river system. The core mechanical failure comes down to 253 dams impounding water and artificially arresting 2/3 of a river's natural sediment load. This model illustrates the divergence. Left, a resilient Holocene delta maintained by continuous sediment. Right, the Anthropocene reality, dams choking sediment upstream, the delta shrinking, the lagoons silting over. This missing Earth will be permanently legible as a missing layer in future geological stratigraphy. The Anthropocene manifests as a tangible, physical terraforming event. Today, our lasting geological legacy is defined by the massive physical Earth we refuse to let flow to the sea, as clearly as the carbon we emit into the sky.